Hello everyone, this is Mr. Suman. Welcome to Suman Education Academy. Hope you all are doing great. So in today's class, I'll continue fluid mechanics, one of the very important subject, right? From fluid mechanics, unit 1 is fluid statics. From this particular unit, one of the important topic is capillarity. So this topic is really very important. So let us understand what exactly capillarity and the expression for capillary rise and expression for capillary fall. So before going for expression for capillary rise and capillary fall, let us understand what exactly capillarity first. So coming to here, we are aware what do you mean by addition and cohesion, right? Mostly all are aware of this too. So coming to in capillarity, if this is the point number 1, if the liquid has greater addition, means addition is greater than the cohesion, then the liquid will wet the solid surface. Solid surface, right? And it causes the rise of liquid. It causes the rise of liquid in the tube. So this I will show in figure. And next, coming to next point is the very first condition is what here? If the addition is greater than cohesion, then the liquid wet the solid surface, right? And here, thus condition causes the rise of liquid in the tube. Now, for example, the second condition is if the cohesion is greater than addition, then the liquid will not wet the solid surface. And the liquid surface will be and the liquid surface will be depressed at the point of contact. Point of contact. That means it is fall. That means it is fall of liquid in the tube. So what is rise of liquid in the tube and the fall of liquid in the tube, that I will show in upcoming figures in expression for capillary rise and capillary fall. So here the very important point that we need to understand, here the phenomena of rise or fall of a liquid surface, the phenomena, let me write here. So here two conditions are given. One is what? If the addition is greater than cohesion, then the liquid wet the surface, solid surface, right? And which causes the rise of liquid in the tube. If cohesion is greater than the addition, then will not wet the means what? The liquid will not wet the solid surface, right? And the liquid surface will be depressed. That means fall of liquid in the tube will be happen. So here the very important point is, so such phenomenon of rise or fall of liquid surface surface is known as capillarity. Is known as capillarity, right? So, and in generally, the capillarity here, especially in SI units, it is expressed in meters, in meter of liquid or millimeter of liquid. So I hope you understand the conditions here. So this rise of liquid surface, let me go for choose new page. So the rise of liquid surface, the rise of liquid surface is known as capillary rise. Capillary rise. And here the rise of, sorry, it's not about rise, the fall of the liquid surface is known as capillary depression, or we can call it as capillary fall. Capillary fall. Now we understand what exactly capillarity and what is capillary rise and what is capillary fall. Now let us go for the expression for capillary rise and capillary fall. So the first case is expression for capillary rise. Really very interesting topic. Look at here what I am doing. So I'm considering one small vessel. I'm considering small vessel here, right? So this vessel contains a liquid, say water, contains a liquid that is water. There is a amount of water inside of this vessel. Clear? So now what I will do here, inside this water, I am considering a glass tube of small diameter. So let me choose some different color. Inside, so here inserting a small diameter glass tube. Right, the glass tube which is having small in diameter. Clear? And very important point is, for example, this is a surface of the liquid, right? And here you can see the curve how it is forming. Clear? And then due to it was clearly mentioned, now this is called, the liquid is called water, right? This is the liquid which is a water. And here what we are doing, when we are inserting this small diameter tube, the tube diameter will be D. Let me write here. D is diameter of the tube. Clear? Now, when we are inserting this small diameter of the tube, and very important is this tube is open at both the ends, right? And when we are inserting in a liquid, then definitely there, the water rise will takes place. The water rise will takes place, and then here there is a concave will be going to form. Here the concave will be going to form, and this level of the liquid from this surface is equal to measuring in terms of with the letter H. So height of the liquid is H in the tube, and then this particular concave, this is called surface tension, and which is denoted by sigma. I'm projecting both the sides here, right? Sigma. And here, as it was clearly mentioned, this is called concave, right? And look at, this is called the vertical tube, right? And with respect to the surface tension, this angle is equal to theta, right? So let me resolve the surface tension. So here this tangential surface tension will be resolved horizontally and vertically, right? So this theta is with respect to vertical, then this one will be sigma cos theta, and here it is horizontally sigma sin theta. See, very basic mathematics, right? Then here let me write, because there I have taken sigma, theta and h, right? So what the tube diameter is D, and here h means the height of the liquid in the tube, and the sigma is surface tension of liquid, and here what is left? Yeah, theta. Theta is the angle of contact between liquid and glass tube, right? Liquid and glass tube. Clear? So what we need to do now? Here clearly mentioned key expression for capillary rise. So capillary rise means, here look at what is the level of the or amount of water is raised inside the tube, that we need to determine, that is H, right? So we need to determine this H. So we are aware of what is the diameter of this tube. So from this we can get the area, right? And we must calculate the weight of the liquid of height H, right? So, and we have surface tension, then we have to know what is the tensile force, because here it is pulling, right? What is the tensile force? So look at now, here we have a figure, I am taking, and this figure is capillary rise, and here the adhesive means adhesion forces are greater than cohesion, right? Greater than the cohesion. Clear? So therefore what I am doing now, very first let us calculate what is the weight of the liquid of this particular height h inside this tube, right? So let me choose some different color. I'm going very slow because in few minutes also we can complete, within 5 minutes we can complete this topic. But for better understanding purpose, just I am covering each and every points. So here the weight of the liquid of height is h in the tube, right? In the tube, because look at here, we need to calculate what is the height h, then we must aware of this particular weight of the fluid and this surface tension. Clear? So very first we are calculating what is the weight of the liquid of height h in the tube. So generally, we know, for example, the weight which is denoted by capital W. The weight is equal to mass into gravity, right? So we know the density is equal to mass to the volume. Then here, mass is equal to what? Density into volume. So let me consider here, mass is equal to density into volume into gravity. So let me write here volume into rho into g. Then volume, again I am writing here, the volume is equal, generally volume equation is area into length. But instead of length, what we are considering here? Height we are considering. Then volume will become the area, because it is a tube, right? Then area will be pi by 4. Otherwise, let me write here the area into height h into rho into g. Clear? Now the area is pi by 4 d square into height is h into rho into g. So this is equation number 1. But let me give one more alternate procedure for calculating the weight. So generally, specific weight, for example, which is equal to weight to the, already we are aware, right? Weight to the volume. Then here weight is equal to what? From this above equation, weight is equal to specific weight into volume. Specific weight is always density into gravity. The volume is area into, the length is nothing but here height. So we have got same equation now. So through this also we can develop this equation. Clear? So we have got the equation 1. So we got the, what is the weight of this particular portion of the height. Clear? Now after getting this, look at to the figure. Here we have surface tension, that is tangential, right? But we are considering which one? The vertical component we have to consider, because here the surface tension is resolved into horizontal component and vertical component. So here angle is with respect to vertical, then we have to consider vertical component. So let me choose, next one is vertical component of the surface, and that is tensile force. So generally we are aware surface tension denoted by sigma, which is equal to, what is the formula? Force to the circumference. Circumference is pi into d, right? This is general. So from here we can get the force which is equal to sigma into pi into d. Clear? But this sigma which is tangential, so when it comes to vertical, it is sigma cos theta, right? Then what we need to do here? The tensile force F, which is equal sigma into cos theta, we have to consider into pi into d, right? So consider now, this is equation number 2. For balancing, we have to equate equation 1 and 2 here. So equating equating equation 1 and equation 2, right? What is equation 1? What we have got? Pi by 4 d square, pi by 4 d square into h into rho g, right? H into rho g. This is equation 1 equal to equation 2 is sigma cos theta pi d. Sigma into cos theta into pi into d. So here this pi will get cancelled. Square and diameter will get cancelled. So what is left here? Rho gh by 4, which is equal to sigma cos theta, right? And what we need to determine, clearly I was mentioned, we need to determine h, that is height of the liquid in the tube, right? So here h is equal to, the denominator will multiply here towards right hand side, so 4 sigma cos theta divided by rho into g. And sorry, here I forgot, here square diameter and square got cancelled, right? Here one more d is left, so let me choose diameter d here, then rho g d. Clear? So after getting this, so this is the actual equation for the capillary rise. This is the equation applicable for capillary rise, and it is in terms of meters, right? So let me write, it is applicable for capillary rise. Clear? And very important note point is, very important note point here, this angle, we have a theta, right? This angle theta, generally, it is between water and glass tube. Water and glass tube is approximately equal to 0. So we are aware the cos 0, which is equal to 1, right? So therefore we can write the equation, above equation will become, because when this condition is applicable, if the liquid is water, then this condition is applicable, means the angle will not be given, then we can assume which is equal to 0. Then h is equal, what will become? 4 sigma by rho g d. So this is the equation, right? If theta angle is given, then better use this equation only for capillary rise. If theta angle is not given, instead of that, if the given liquid is water and then glass tube, then we definitely, we have to assume theta is equal to 0. Clear? And now it is about capillary rise. Now what next? We need to understand what exactly capillary fall now. Now look at now. Next one is capillary fall, right? So again, let me choose the diagram here. Let me choose some different color. I am considering one vessel. See, I am drawing with free hand, so the diagram may not be neat. Please try to understand. Right. So here again, what we are doing now, we are using considering a glass tube, which we are, and here the liquid is mercury, right? And inside which what we are doing, we are dipping this glass tube, right? And here this is the level of the mercury. See how it is falling, right? And generally here we know cohesive forces are more here when compared to adhesive, right? Then here this particular, from this surface, here this inside we have a mercury, Here the liquid is mercury. So we all are aware specific gravity of mercury, right? Already a very long back we have studied. So here this one is forming convex structure. It will form the convex structure, right? And here at this particular area, there are pressure which is acting P, and here the surface tension is sigma, and the angle which is greater than 90 degrees. So this is called theta, and here from the surface of this mercury to this level, which is denoted by H, and let me write this figure is applicable for capillary fall. So very simple, instead of water, what we have considered here, mercury we have considered, and this is called the capillary fall, and where cohesion is greater than the addition, right? And due to this reason, right, the convex is forming. And here what we need to calculate, first we have surface tension, and next we have the pressure forces, right? So let us calculate force due to pressure. Force due to intensity of pressure. So generally pressure, we know the equation, pressure is equal to force by area, right? So what we are calculating here, we are calculating force, then force from this above equation, force is equal to what we will get, force is equal to pressure into area, right? So let me write here, the pressure is P and area is A, and this area is pi by 4 d square. So it is pi by 4 d square. So this is equation number 1. Because it is a depression, right? So you can't see any fluid inside. Clear? Now let us consider next one is surface tension. So force due to surface tension. Force due to surface tension. So again, here already before, I have written here very clearly. Otherwise, let me write again. Surface tension is equal to force by circumference, that is pi into d. Then force is equal to sigma into pi into d, right? So here sigma in terms of, again, the angle is with respect to this, right? Then it will be cos, sigma cos theta into the circumference is pi into d. So this is equation number 2. So equating equation 1 and 2. So equation 1 is P into pi by 4 d square, right? And next, which is equal to sigma into cos theta into pi into d, right? So let me write again, P into pi by 4 d square, which is equal to what we have, sigma cos theta pi d, sigma into cos theta into pi into d. This is called pi into d circumference, right? So here again, what we need to calculate in this particular depression or fall, again we need to calculate the h, that is called height of the liquid which is fall, right? Now we know the pressure also equal to rho into g into h, right, into here pi by 4 d square, which is equal to sigma cos theta into pi into d. So here pi will get cancelled, square and diameter will get cancelled, So what is left here? Rho GH into D divided by 4 divided by sigma, equal to sigma cos theta. Then what we need to calculate? H we need to calculate. H is equal to what you will get? 4 sigma cos theta by rho GD. So this is the equation. But just observe here, do you have any difference in these two equations? What we have got here is 4 sigma cos theta by rho GD, and here also we are getting 4 sigma cos theta by rho GD. But here the difference is, here we are calculating H, that is height of depression in tube, and very important is here theta is greater than 90 degrees. But here the theta is, here this angle theta is less than 90 degrees. So this is the difference, right? It is less than, because look at the figure, it is less than 90 it is. So this is total 90, right? So it is less than 90 only. But look at here in this figure, for example, it is 90 degrees, but it is more than, right? Then here clearly written this theta is greater than 90 degrees. So definitely the values will be going to change. And again here there is a note point, very, very important. The note point is the value of theta. The value of theta. Here which liquid we have considered? Mercury, right? For mercury. And glass tube. Is 128 degrees, or you can consider 130 degrees. Clear? So this is about the capillary. This is capillary fall or depression, right? And this is called capillary rise. So with this, thank you very much. In next class, we'll solve couple of problems on this particular topic. I hope you definitely understand this topic. So thank you very much.